Hello, good afternoon, everybody. Today we will continue our discussion for constant acceleration. In the previous lecture, we have derived the equations we can use to solve constant acceleration problems. Today we will continue to work on that, and in particular, we will look at a free fall type of motion, which is an example of constant acceleration, but it's just in the vertical direction. And we are also going to do some math for vector analysis, because when we're dealing with motions in two different dimensions, we need to know how to break it down into two different directions. So first of all, let's take a look at the checkpoint questions you guys have already done. This is the question. Since you have already done this, I will go through this relatively quickly. Okay, so we see a ball going down the incline, and it's telling us it's moving with a constant acceleration. So it's going to speed up all the way through, right? It moves 1 foot between 0 seconds and 1 second. Now, how far would it move between 1 second and 2 seconds? So since it's asking us about how far, it's a question about the magnitude of position or the magnitude of displacement. We are going to use these kinematics equations, right? The two equations, one is about the velocity, one is about acceleration. One is about position. So we're going to use this equation. So from the initial moment, which is t equals 0 to t equals 1 second, it moved 1 foot. So in this case, this is 1 foot. It traveled this far. And it's starting from rest, right? Initially at rest. So V initial is at rest, or V naught is 0. So 1 foot is 1/2 acceleration times time. So between with the 1 seconds, you have moved 1 foot. So this is the first information, the first sentence tell us information about its acceleration, which is 2 feet per second square. That is acceleration. So with that information, we can find out how far it will travel between 1 second and 2 seconds. So from 1 second to 2 seconds, this is what we're trying to look for, right? And we want to know what is x2 minus x1, the change in position between 1 second and 2 seconds. And that is going to be v, velocity, initially. Here, my initial is 1 second. That is the moment I decide to look at, to choose to look at this motion. So that is velocity at 1 second. And it traveled for a total of 1 second, right? So 1/2 times acceleration is 2, and another 1 second. Now velocity at 1 second, you can get it from this equation, which is acceleration. Velocity at 1 second is acceleration times time, the first section of time, from 0 to 1 second. So that's just going to be 2 feet per second. So if you plug this here, I get the total distance traveled from 1 second to 2 seconds is going to be 2 feet per second times 1 second plus 1/2 times 2 times 1. And that's going to be 3 feet. Okay, so C is the correct answer. Okay, in fact, you can see that if it's constant acceleration, the position follows. Initial position is 0, initial velocity to be 0, and the final position is simply a 1/2 at squared relationship, right? So A is 2, so it's just going to be t squared. So 1 second, 1 feet, 2 seconds, 4 feet, 3 seconds, 9 feet, 4 seconds, 16 feet. So that's just going to go, so you can see the space between 1 second is much, much larger as you go on. And if you plot it on the graph, you probably notice that it's going to be like a parabolic type of curve. Okay, So that is our checkpoint question. Let's also solve one example problem for a constant acceleration before we do the free fall. So here, it's a very straightforward question. Draw a picture and try to set things up yourself. So we have a driver of a car going 30 meters per second straight on the road. And the driver spots there's a deer right here. So I'm gonna just draw this to represent the deer to save time at 75 meters ahead. So it needs to apply an acceleration to stop the car. So if the car is moving this way with an initial velocity, you think the acceleration should be applied in the backward direction to stop it. So in order not to hit the deer, so the car should be stopped at 75 meters. Okay, so I'll give you a minute. You can try to, if you have your notes right here, you can try to set things up, label your quantities, and think about what is the physics involved, what kinematics equations should be used. Okay, I'll give 1 minute to think about this. Okay, let's take a look at this together, and hopefully you have drawn some kind of a picture and you have labeled your quantity. Drawing a picture will help us to visualize the process. As you reading the word to word, and you translate these quantities and label it on your picture. Okay, so I have the car here, the deer here. I wanted to label the quantities. I have done a few of them. I put the velocity here. I also want to add the axes, so I could know what is positive or negative. So I can choose to put my origin here. Now you can choose to put it at where the deer is, or put it wherever you want. That's totally fine. That's up to you, but I just choose to put it where the car is. And I'm gonna choose to be, the positive directions is to the right, in this case, to the direction of where the deer is. And this is where the deer is. So, and the car, and the question is what acceleration is needed. So this is the unknown quantity. So you want to put your known quantities down, and you also wanted to write down your unknown quantities. So other than the velocity initial, so we know a few known quantities. In this case, we're looking at the motion of the car that's involved. I know the initial velocity of the car is 30 meters per second. I know the initial position of the car is at 0 meters, because that's where I set it. And there is something else that's kind of more implicit. If the car starts here and end up here, the car's final position is at 75 meters. And there's another information that's kind of hidden. What is the velocity of the car final? So what do you think the velocity, the final velocity of the car is? Is it given in the problem?
0.
It has to be 0. That's implicit. That means that in order to not hit the deer, you need the final velocity to be 0 when you are at this final position. Right? So that's not directly given, but reading from the problem, we would know. So given these known quantities, we wanted to solve for the acceleration that is needed for these known quantities. Okay, so what is the physics that's involved? That's sort of our third step. We are analyzing motion of the car, and the car is moving with constant acceleration. So the physics is we need something that deals with constant acceleration, right? And for constant acceleration, I list three equations for you guys. We have derived 3 of them. And which one do we pick depends on the information that's given. So which one of these do you think we should use to solve for A?
Third equation.
The third one, this seems to most straightforward because we already know position, we already know velocity, and we don't have any information about the time. So we're gonna use this one. Okay, so let's plug in our quantities. V final is 0, initial is 30, acceleration is something I want to solve for. Final position 75, initial position 0 meters. I'm gonna put a meter here. So I found my acceleration to be negative 900 divided by 2 times 75. I get negative 6 meters per second square. So I still should have the unit that is correct for acceleration, negative 6, indicating that it is an acceleration pointing to the left, which is opposite to the positive direction that I'm applying. So you need to apply an acceleration that is in the opposite direction of your motion and with a magnitude of 6 meters per second square in order for you to stop completely when you are at the deer. So there you go. That's our equation, and that is our final solution. So that is the example I want to do. Next, I wanted to go into the free fall motion, which is also constant acceleration, but is in the vertical direction. Before I move on, do we have any questions regarding the checkpoint question and regarding this example problem?
Professor, I have a question about the homework.
Okay.
On the homework, there's 2 optional sections, and I was just wondering, like, is that extra credit or is it just practice?
Optional means it's just practice.
Okay.
Mm-hmm. Okay, so let me, next I want to show you, switch my shared screen. I want to show you something we have all seen. Oh, wait a minute, I do still want this screen, but I just need to bring something up. Okay, the physics of cartoons. I want to just show you just a few seconds of the clip real quick.
The Physics of Cartoons, Part 1. Law number 1. A character will remain suspended in space until it looks down.
So obviously, that's being ironic. That is wrong physics, and a lot of times in not just in our movies, in our cartoons, that's made more dramatic. So the law of cartoons, if we put a quotation mark on it, law number 1 is anybody suspended in space will remain in space until they're made aware of their situation. Of course, we know that that is a violation of physics laws, because if you put something in space and you just drop it, it's going to fall because there's gravity. So today we will look at how to calculate free fall motion that is in the vertical direction. Is a type of constant acceleration. So people actually have been studying the motion and have formulating their ideas ever since Aristotle. So back in Aristotle's age, he had this idea about how things move, right? And it can be described sort of using a poetry. There's a natural place for everything to seek, as heavy things to go downward, fire upward, and rivers to the sea. So it is in Aristotle's idea that heavy object will seek their natural place faster than a lighter object. So back then, people think heavy objects falls faster. And we tend to observe that somewhat in the real life, right? If you have a piece of foam, which is very light, you have a metal ball, now the metal will fall faster. So Galileo took an interest in this. And when he was teaching math at University of Pisa, he took interest in this, and he decided to do a experiment to test Aristotle's idea. But his idea was a little bit modified. He think the rate of falling will be proportional to the density of the balls. So not quite the weight, how heavy it is, but the density. So he wanted to test this idea. The story goes that he dropped 2 balls from the Leaning Tower of Pisa, one heavier, one lighter, just to see if it is indeed proportional to its density. This is really important because before Galileo, there was no such things as a controlled experiment. Those things may seem so natural and obvious to you nowadays, but back then people have not thought about doing an experiment. And he took an interest in do that. To his surprise, with a little correction due to the air resistance, the speed when it's close to the ground is nowhere proportional to the density, and they seem to hit the ground at the same time. That is very surprising to Galileo. So nowadays we know that everything that is falling on Earth, if the gravitational force, gravity is the only force applied on the ball, then it's all going to fall with a constant acceleration, and we call it little g. It's called gravitational acceleration. So g represents for gravitational acceleration, g, which is a value 9.8 meters per second when you are on Earth. Now, g is always positive. It's magnitude for the free fall acceleration. Sometimes if we define our positive direction to be upward, then we will end up with a negative acceleration. So it's a negative g. So if I'm saying, okay, I want positive, this is a positive direction, but my acceleration is downward. So I'm gonna say my acceleration is going to be negative g, which is negative 9.8 meters per second squared. Notice that it's not exact 9.8. Different places on Earth will have a slightly differences in terms of the acceleration, but overall, we just take this value as an average. And also, if you are really, really far away from Earth, obviously that g will be smaller. But here we're looking at a near Earth approximation. So anything that is still within the Earth's gravitational pull, we're gonna just treat it as 9.8 meters per second. Now, obviously, if you go away and you have escaped the Earth's gravity, you're not gonna experience acceleration anymore. Okay, so this is for free fall. Galileo proposed all objects are subject to the same acceleration when they are in free fall. It's really just a particular type of constant acceleration, so it's moving in the vertical direction with a constant acceleration, meaning that things will speed up at a constant rate. Even if it's called free fall, things can still be moving up. You can throw a ball upward and throw it upward, but as long as there's no other force acting on it, as long as the only gravitation field is feeling it from the Earth, then we call that is a free fall type of motion. It simply just means the acceleration is going down. Okay. All right. So since it's a constant acceleration, we have already done that. This is really just applying something we already know. So let's look at a quicker question. I'm sorry. All right. I will do a breakout room for you to discuss this question for about a minute or so before I bring you back, and take a screenshot first before you go to your breakout rooms. Okay, I have pretty much everybody's votes. Most of it was coming in, so just a few seconds for any last minute vote. Okay, I'm going to go ahead and close the poll, and then we can take a look. And here are our results. majority of you voted for B, so 9.8 meters per second. And there is some portion of the answer choose for A, which is larger. So once we throw an object downward, right? So we do agree, and I do agree with you. If we throw something down versus if we just drop something down, we release something, the one that you throw down will reach the ground faster. Not because it has a bigger acceleration, right? It's still going to have the 9.8 meters per second squared acceleration because it is in free fall. Once you let go, you are no longer applying a force on it. It's experiencing something only the Earth's gravity. So what is that you're really doing by throwing it down that make it go to the ground with less time? Yes, so I'm seeing that people answer this with a higher initial velocity. Excellent, but with the same acceleration. Yes, so if you drop something, it will start v equals 0 and an acceleration of 9.8 meters per second downward. But if you drop something, you give an initial velocity that is not 0 and is still accelerating downward. Very good. So the correct answer is B. So don't be confused by you throwing it downward. You're simply giving it an initial speed. Now let's look at this question. Again, it's with graphical representation. That seems to be something people tend to have more difficulty with. You throw a ball vertically upward, okay, and the ball moves up, reaches highest point, and then goes back down. So which one of these graphs representing the balls? Correct, acceleration versus time graph and velocity versus time graph. So you see that in this problem, it has not really defined a positive direction for you. All you need to do is you choose the acceleration velocity graph that is consistent in its how positive and negative are defined. So I will let you again discuss this in your groups for about a minute or two. Again, take a screenshot before you leave for the breakout rooms. Okay, another 15 seconds. Let's put in your final vote, 15 seconds. Okay, I'm going to go ahead and close the poll, okay? So here are the results. And let's take a look and talk about this together. Anybody would like to share with us what they discussed? There are two different graphs we need to choose. How did they decide which one correctly represent the situation of the motion?
Our group basically talked about how the acceleration whenever you throw a ball up is always negative
Okay.
because it's going against gravity. So it'll always have that negative acceleration of gravity.
Mhm.
And then eventually it'll hit a point where it stops
Mhm.
moving, which will make the velocity zero. So it has to be zero at some point. So it can't be d. And then it'll start going down whenever it hits the top of the, I guess, parabola of the graph. If you thought about it as a graphing function, eventually it'll start being negative velocity. And so that's why we chose B.
Ah, thank you, Andy. So you said the acceleration is negative always. Notice that we haven't really defined positive or negative, but as long as it's consistent with your choice of graph, you're right. So if if implicitly A and B and C all had chosen velocity to be positive to begin with, right? They're positive here. So that indicate for acceleration to be consistent with the positive choice of going up, because you're throwing the ball up, it's got to be negative. So it has to be negative constant. And at this point, you reach a zero, stopped. So from here, you stopped, and then you come back down. So keep going, speeding up for the rest of the motion. Yes, very good. So B is correct because the acceleration and velocity are consistent choices. Now, obviously, you can see the ball can no longer be going up, right? For the second half. So that's why this is wrong, and this one is wrong as well. I also want to discuss this question that is on your homework. This is one of the final, there are a lot of sub-problems, little sub-problems that are leading up to this process, but I want to just solve this last sort of a bigger question. So it's about they pass each other, they meet each other, and that is a very common type of question you will see. So in this case, you have a blue ball that's been throwing upward. You have a red ball that's been throwing downward at different times, and they're going to meet in the air where they're at the same height. So we wanted to find out what is the time it takes for them to be in the same position. I want to demonstrate how to solve this problem for you. Okay, let me see if I missed any. Okay. And notice that I will have different numbers than you because everybody is getting different numbers, but I'm just going to use these numbers as an example. Okay, so let's first of all draw a picture to visualize the situation. The picture sort of is already given. You can use this and add your quantities to it, or you can start drawing it again. I'm just going to draw it again. So you have a blue ball here, and you have a red ball here. Okay, the blue ball is at a height of 0.9 meters above the ground. So I wanted to label this quantity as, so I'm going to choose this to be my positive axis. And there, this is my origin is y equals 0. So the blue ball will have a initial position, right? So y position. So here I'm using y instead of x because it is a vertical direction. I do y, but the same kinematics quantities is applicable in the y direction. So I'm going to say y of the blue. Initially, I'm using two sets of subscript to show it's the initial velocity of the blue ball is 0.9 meters. Okay, and you give it an initial velocity, VP, initial is 22.4 meters per second. So that's my quantities. I'm labeling it. The initial position of the red is at, as you read it, you can translate these into your problems, is 28 meters. And it's throwing downward, so which means the velocity of the red initial is 10.1 meters per second. Okay, so I have labeled my quantities. I have defined my coordinates to be like this, going up to be positive. And now I want to describe the physics. The motion of the ball. So the motion of the blue and the motion of the red, they're all in constant acceleration motion, right? So what type of motion would you describe? Would you use to describe them? What kind of motion?
Linear?
Is moving with a constant acceleration. Yes, so in the sense that your velocity is changing in a linear way, and it's just going to be free fall. It is free fall. It is the type of motion we did today. Okay, so they're in free fall. The question is, so the question of the problem is, how long after the blue is thrown are the two are in the same height, which means if they're in the same height, which means the final position of the blue is the same final position of the red. Okay, so that is how I translate it into words. Mathematically, it's going to be V blue final equals V red final. So that is the mathematics expression for the word. Okay, so the rest of it is to plug in the position for blue, plug in the position for red, and solve it. So the blue final, okay, this is the kinematics equation, right? Final position is initial plus what? You still remember those equations?
Initial velocity times time.
Yes. Okay, so initial velocity of the blue times time, that how long the blue has traveled. So I'm going to just leave it as time here. Plus, what else?
Plus 1/2 acceleration times time squared.
Okay, acceleration here. I realize I haven't labeled that. Acceleration is negative g. We're going to be 1/2 negative g times time squared. Okay, so I can do the same thing for the red. Is the red initial plus the red speed times the time of the red. Okay, so is the time of the red the same as the time of the blue? So 2.7 seconds after the blue is thrown, a red ball is thrown down. So the red has traveled with a smaller amount of, less amount of time. It's going to be, if the blue has traveled with t, how do I represent the time for the red?
T minus the seconds that it started with.
Yes, thank you. T minus 2.7 seconds for the red, and the rest is the same. T minus 2.7. Okay, so you need to set these two equal to each other, right? So which means you need to set these two are equal, and I'm gonna plug in numbers for these terms. So the initial position of the blue is this. Initial speed for the blue is this times time minus 0.9. meters per second squared times time is equal to initial position of the blue is 28.1 meters. And this one is flowing downward with a negative 10 meters per second times a less amount of time minus 4.9 times t minus 1. So it's going to be a quadratic equation. To simplify and blah, 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 eventually to do some math, I'm gonna eliminate the process. Eventually you'll get, simplify it to this. Where t is going to be 3.11 second. Okay, so that's the answer for these set of numbers that I'm giving. If you have different numbers, you need to plug in your numbers. So, okay, so we can see that. All right, so I wanted to talk a little bit about these labeling these quantities. There are different choices. So sometimes when people label the velocity vector, right, they show the direction by the arrow, and they simply just saying the magnitude here. But there are different ways of doing this. Here, for example, again, I've showed the velocity is downward and the magnitude is this much. But if you want it to be, but then you have to remember when you are plugging in your velocity here, it's a negative velocity. Right, you need to think about the direction. You need to plug in the negative number here. So you might as well put a negative here, just so that you don't forget about putting that negative sign later on in your equations. And again, for acceleration, right? If you have done, okay, acceleration here, if you say something like this, it might be fine. You could, if you remember to putting a negative sign later on, like if you remember to put a negative here, it might be fine, but you may forget and you put a positive here, which will lead to a wrong solution. So I recommend you can just put your negative sign as you're writing it down, just to avoid possible mistakes. Okay, so that is my solution for this homework problem. Next, I want to talk a little bit about math, about how we break down vectors. We already talked a little bit about vectors. We will do a little more today because knowing these vector analysis can help us solve motions in 2 different dimensions. You know, we have a more complicated problem we can tackle. So before I move on to talk about vectors, do you have any questions so far? Okay. All right, so let's look at our vector presentation. So we have already talked about how we represent a vector. For example, in terms of your position, you can tell people by saying, oh, I have moved 4 meters to the right. So let's say this is you and you're walking around. And you say, I moved 4 meters to the right. And then I moved 3 meters to the north or forward, whichever you wanted to find that direction. So you end up at 5 meters away from where you started. But there are different ways to describe it or to represent it. The one way is to tell people about your components. So you can say this final position is has a component of 4 in the I hat direction, horizontal direction, and a component of 3 in the vertical direction. So you'll write it in this format: 4 I hat plus 3 j hat. So these hats, vector hats, are unit vectors. They don't have magnitude. They're only telling you the direction, right? So 4 to the right and 3 above. Or you can tell people about you are at 5 meters away from the origin and you are at an angle of how much above the right direction. You're 36 0.9 degrees above the x-axis. So there are two equivalent ways of representing the same vector. People see this and know which point you're talking about. So in general, now if you have a vector, you can say this is a component a hat, a plus b, ai hat plus b, and this is how you calculate the magnitude. Magnitude meaning the length of the vector. So how long is here to here, how long it is. That is a hat. So a magnitude. And you can calculate the angle by looking at the tangent theta, which is b over a. Okay, so given one type of expression, you can figure out the other, and vice versa. Given this expression, you can figure out the other one. They're equivalent. So if you have a vector addition, we did a head-to-tail method, right? We did this one plus this one. You add them up, give you this one. But you can also add them up as if you were doing sort of algebra. If you know the components, you can add them component by component. So for example, if A vector is 2i hat plus 3j hat, and B vector is 4i hat plus minus 1j hat, then when you add them up, you add each component just like how you add numbers. You get 6i hat and you get positive 2j hat. So this is like doing algebra, you just add them up. Because once you break it down into components, they are no longer vectors, they're just numbers, they're scalars. Then you can just simply add them up. So sometimes people find doing it component by component is easier than the head-to-tail method. So whichever makes, it is easier to solve, we wanted to be able to use that method. So if I sort of draw this vector addition on the graph, my A is 1, 2 here, and 1, 2, 3 here. That is my A, okay, this is my A. And my B is 4 here, and negative 1 here. So this is my B. And C is 6 and a 2. C is this. But you can see that if I do the head-to-tail method, it's like I can move B up parallelly, or I can follow a parallelogram between A and B, and I get, this is my C, okay? So let's practice doing this component by component by looking at this question. So I have 3 vectors, but they add up just like how you add 2 vectors, right? A and B and C, they add up to be a new vector S. So I'm asking about the S component, X component of the S. I'll let you guys take a screenshot of this before I send you to breakout rooms. Again, this will take about a minute or two to figure out. Someone asked and missed the equation that was on the slide above. Do you still want me to slide up? Do you still need this? Okay. So
Yeah, can you?
is this slide you're looking at? Okay. This one, Mark? Okay. So I'll stop here for a second for you to take a look. Okay, and then I'll bring things back down. Okay? This is a question, take a screenshot, and then I'll open the breakout rooms.
Oh, Professor, do you mind scrolling up to slide 103 for a second?
Okay, 1 second. Oh, can you do that? I couldn't. Yeah. This one?
The one above that. That's perfect. Thank you. All right, I got it. Thank you.
So let's go for another 15 seconds for the vote to come in. Okay? Okay, let's take a look. This is this is our results. And we want to find out the value for the x component of s. Anybody would like to tell us that the strategy that you use to answer this question? Do you have to do the head to tail method, or do you add them up by components? What strategy did your group use? Doing head to tail it might be a little tricky. Yes?
I'm not really sure if this is the right way to do it, but since it's just asking for the x component,
Mhm.
I assumed that it only wanted us to measure like the from left to right. So like for example, like A goes 3 like from left to right. So and all the other ones also do 3. And since their vectors are pointing the opposite direction, it's basically like doing 6 minus 3 or 3 minus 6, which is -3.
Ah, okay. So this is 3 to the right, and this is our 3 to the left. So let's just say that's -3. Okay, and yes, B would be 1, 2, 3 to the left again, and then another -3. Yes, very good. Thank you, Andy. So S of x will be AX plus BX plus CX. You add up the component just like scalar. So that's 3 to the right and -3 to the left, 3 to the left. I realize we haven't really defined a positive or negative direction. Yes, so I should have said positive is to the right, is positive direction. So that these are negative. So you get -3. Very good. Okay, so you can see that breaking it down by components actually help us to solve this problem very quick. Otherwise, we would, if we do have to tell, it's a little bit more confusing, right? You have to move these vectors and manipulate them on the graph. Now let's look at another one. So again, you were given two vectors A and B, and they give you the component of them, each of them. And you want to know the vector s, which is a minus b. A minus b is as the same as a plus minus flipped b direction, minus b. And okay, to be not to confuse you, these are answer choices A, B, C, D. These are arrows. Okay, so what is the direction of the vector is pointing in certain direction. So these are not a vector A, B. These are answer choices A, B, C, or D. Okay, again, you have about 1 to 2 minutes for this question in your breakout rooms, and make sure you take a screenshot of the question before you leave. Takes about another 20 seconds for us to finish voting. Okay, any last minute vote? Okay, I'm going to go ahead and close it. So here are our results. We want to be able to draw sort of roughly the direction for this vector. Let's work it out together. Of course, you can draw the A and B, right? That's one method to do this. A is here, 1, 1. B is -2 and 2. Right? You can add them up to see kind of in what direction they're pointing at. Or we can do S. X would be AX minus BX. So that would be 1 minus 2, negative 2, that is 3. S of Y would be AX or AY minus BY. It's going to be 1 minus 2, that's -1. Okay, so 3 and -1, right? 1, 2, 3, and -1 should be in this direction. So that would be your S. Okay, so you can see that S plus B give you A. So S plus B give you A. You can also confirm it by using the head to tail method to see if that is true. So, but you can see by doing this algebraically, component by component, it's very easy. It's very quick. So answer is D. That is correct. Very good. Okay, so the last question, the last little bit of today's class is I want to show you another example. How can we do vector addition by components? Now, sometimes if you were given instead of X and Y directly, but if you're given the R and theta, you can break it down into X and Y yourself. So for example, if I give you A vector to be 6 in magnitude, 120 degrees. So this is what A is. It's 120 degrees and 6. So that is your A vector. Okay, so that you can find out the AX by doing A cosine theta and AY by doing A sine theta. Okay, you can find your BX the same way, is B magnitude times cosine theta. That's your X component for B, and B sine theta for B to do the Y component. And you can again find the overall C vector by doing component and component and simply add them up. So for example, if I present you with this example question, we have a boat. Originally is located at the position 5i, 4j. And then the boat sails for 60 degrees north of east with a constant velocity 2 meters per second. After 5 seconds, where is the boat? So what is the boat position? So you can see that involves motion that is in 2 different dimensions. And one way to do this is to look at component by component. Okay, so the boat is originally here. That's where the boat is. And it has an initial position that I use R to represent it. 5i hat plus 4j. That is where you are. You are 5 to the east and you're 4 to the north. And you're driving with 60 degrees north of east. So this is 60 degrees. You're driving with this blue angle. blue arrow, and you have a speed of 2 meters per second. So at 5 seconds. So you know that from here to here, the type of motion is constant velocity, right? So you can easily calculate the distance you traveled during the process, the distance you traveled, delta, you can see delta x or something, or delta r, changing position, and just use r. Is velocity times time, and it's going to be 2 times 5, that is 10 meters. Okay, so you've gone 10 meters this way. And it's asking where you are with the final position. So you want to be able to tell people where you are by either presenting your x and y coordinates, or you have to tell people your how far away from origin and your angle. So either one of those ways to represent where you are. So here I do this component by component by saying, okay, my final position is simply going to be my initial position plus the change. This is delta. This is the change of position. And my initial position is 5i plus 4j. And my change in position, I also need to represent it using 2 different components. If I don't do it this way, I have to look at you. I have to do, okay, x direction and y direction separately. Okay, so I have to look at how far did I go in x direction, how far did I go in the y separately. But this way I'm able to write everything all together. So your velocity is 2, and it's in a 60-degree angle. So I simply just break it down by 2 times cosine theta. That gives me my x direction, and 2 sine theta gives me y direction. So I will have my change in position, delta r, is v times delta t, and v is in 2 different directions. The x direction is 2 cosine 60 times 5 seconds. That's I hat. 2 sine 60 times 5 seconds. That's j hat. So I end up having 60 1/2, 5 I hat plus 5 root 3 j hat. So this is my change in position is here. And add x hat and x hat together, you get 10 in the x direction, you get y 12.7 in the y direction. So this is where you are, and this is your final location. Now you can see that this follows a head to tail method, right? Initial position, r initial, plus the change, delta r, gives you the final position, which is r final. Okay, so this is an example how to do this component by component. And I believe you have something similar like that in your pre-lecture, where you have to do the component by component for the motion of the object. So that is all we're going to discuss for today, and or for one-dimensional motion. Next week we will talk about motion in 2 different directions. You have a both x component and a y component. So we will do that next week. Okay. So I will see you guys next week. And if you have any questions, we have a couple minutes now, and you can feel free to ask. If not, I'll see you next week.
Thank you, Professor. Have a good weekend.
Thank you.
Thank you, Professor. Have a good one.
Thank you.
Thank you, Professor.
Have a good weekend.
Thank you, Professor. Good weekend.
Have a good day.
Thank you for your time, Professor.
Thank you. Bye-bye.
Thank you.
Thank you. Bye.